No, I'm going to start with this page first. Because I want to ask you one question. If somebody can answer it. What's a radical? Okay, if you're not sure, then you give me an example. Instead of defining it, you give me an example of a radical. Rita? Yes. Anything with a square root, cube root, fourth root, etc. are called radicals. So it's got this little symbol. A check mark with a bar. That's actually called the radical sign. Okay? There's a little number on the outside. We're going to call it n. If there is no number outside, what do we always assume it is? 2, which means what? Square root, right? But it could be 3, it could be 4, etc. We're only really going to focus on 2 and 3. And then there's something inside. Could be a number, could be a variable, could be a combination of both. We call that little number outside the index. And we call the number inside the radical sign the radicand. So you guys are familiar with square roots and cube roots. Just remember that they're called radicals. Okay? When we say the word radical, we're talking about them all. Okay, now I want to just jump back to this, because you're actually going to have to know these to help you work through one part of the first lesson. So let's look at the numbers first, the number columns. First one is perfect squares. Why is the number 1 a perfect square? Because it's 1 times 1. Why is 4 a perfect square? Because it's 2 times 2. What? 9, because it's 3 times 3, etc. Okay? Or we can take the square root of them and get a whole number. That's why they're perfect squares. Why is 8 a perfect cube? Because it's 2 times itself times itself. 27 is a perfect cube because 3 times 3 times 3. 1 is a perfect cube because 1 times 1 times 1. 64, etc. Okay? So those are examples of perfect squares and perfect cubes. But what if they have variables and exponents? Use the same thinking that you just did with numbers. Why is x squared a perfect square? What times itself gives you x squared? Don't overthink. X times x, right? Because x to the first times x to the first is x to the second. Why is x to the fourth a perfect square? Because x to the second times x to the second. If you remember your exponent laws from last year and from grade 9, when we multiply 2 powers with the same base, we add the exponents. This is a perfect square because x to the third times itself. X to the fourth, x to the fifth, etc. Okay? Why is x to the third a perfect cube? Because you get it by going x times x times x. Just like here, you can get it by going x times x. And x to the sixth, why is it a perfect cube? Because it's x squared times x squared times x squared. X to the third times itself, x to the fourth times itself, x to the fifth times itself, We're going to have to know these when we simplify these things. When we simplify radical expressions, we got to be familiar with the numerical perfect squares and cubes and ones with a variable in exponent. But before we do that, we're going to focus on a lot of radicals that have variables on it. That's sort of newish. You guys are used to dealing with just numbers, finding the square root, finding the cube, or simplifying, like we learned how to do last year. What's the square root of 9? What's the square root of 16? What's the square root of negative 25? Negative 5? But negative 5 times negative 5 is positive 25. What's the square root of negative 25? No, can't do that. Can you do it? No. So that means there's no answer. You can't do it. Okay? That's the same with any radical that has an even index. You cannot take the square root of negative numbers. You cannot take the square root, or sorry, the fourth root of negative numbers, etc. Because whatever's underneath must always be greater than or equal to 0. That's very important. You can take the square root of 0. You can take the square root of any positive number. But as soon as you get into negatives, you can't do it. So we're going to use that thinking when we look at these examples. If there's a variable underneath the radical sign, we have to be able to state restrictions. There are certain values of x that we can't use in this question. Let me give you the most basic ones. Can I plug any number in for x and calculate it? Can I plug any number I want in? No, I can't. I can only plug in what? Only plug in? I can't hear you guys. Come on. No, can't you take the square root of 3? It'll be a decimal, but you can do it. You take the square root of 5. I can plug in any. As long as it's 0 or larger. So what I would say here is I can use this expression as long as x, and here's the symbol for greater than or equal to 0. And that's how you do it. I can use this expression as long as whatever I plug in for x, 5 times x has to be bigger than or equal to 0. Now solve for x. How do you get x by itself? Divide both sides by 5. And you get x is greater than or equal to 0. That's the restriction. You can use the expression square root of 5x as long as x is greater than or equal to 0. You can use the next expression as long as whatever's underneath is greater than or equal to 0. How do I solve for a? Plus 5. Plus 5. And that means a must be greater than or equal to 5 in this case. I can use any number I want as long as it's 5 or larger. Because if I plug 5 in, it's 0. If I plug 6 in, it's 1. If I plug anything higher than 6 in, it's going to be positive. But what happens if I plug 4 in? I get negative 1, which I can't take the square root. That's why it has to be bigger than or equal to 1. See if you can do the next one. Same reasoning. You have here. So I can use 8 plus 8 as long as it's what? Greater than or equal to 0. Now solve for A. You get. So in this case, A can be a negative number because when you plug it in here and add 8, it's going to make it positive. Right? So like if I plug in negative 8, well, when I add 8, I get 0, and I can take the square root of that. If I plug in negative 7, I'm going to get positive 1, and I can take the square root of that. If I plug in negative 9, I get negative 1, I can't take the square root of that. So that's why it has to be negative 8 or larger. And the last one you solve the same way. Whatever's under the radical sign, whatever expression, make it greater than or equal to 0 and solve it like you would an equation. So you're going to have to do a couple of steps here. First, we're going to add 3 to both sides and get 2x is greater than or equal to 3. Then we're going to divide both sides by 2. And x must be greater than or equal to the fraction 3 over 2. So this time we take a fraction. But that's how you find restrictions. Make it greater than or equal to 0. Solve. And you get your answer. That's it. Okay? Before I talk about these, anything with an odd number index, so third root, fifth root, seventh root, you can take negative numbers. You can't do it with even roots. You can't do it with square roots and fourth roots, but you could do it with third roots. For example, if I gave you this. What's the cube root of negative 27? Negative 3. And that works because negative 3 times negative 3 is positive 9. 9 times negative 3 is negative 27. So you can take the cube roots of negative numbers. You just can't do the square roots. For these ones, there's no restrictions. You can plug in anything you want. Why can't I plug anything I want into this one? If I plug 1 in, what's 1 squared? And then take the square root of 1. What do you get? Square root of 1. Thank you. Okay. If I plug 2 in, what do you get? 2. Because 2 squared is 4. Square root of 4 is 2. If I plug negative 2 in, what do you get? What's negative 2 squared? Be careful. Negative 2, the whole thing, squared, is positive 4, which you can take the square root to get 2. Okay? Whenever we square, I can plug any number in I want, because as soon as I square it, it becomes positive, right? Anything squared becomes positive. Which you can square root. and y is the cube root of negative, sorry, the cube root of x. All doesn't need any restrictions with cube roots. X can be negative, 0, or positive. Which means that represents all the possible numbers that are in existence. The negative, 0, and all the positives. So before we even start dealing with these things, you got to think about restrictions. Now we're going to start dealing with them. And it's kind of like when you first learn fractions. One of the first things you learn how to do with fractions is reduce them. Then you learn how to add, and then subtract, and then multiply, and then divide. We're going to do the exact same thing with radicals. We're going to learn how to, we don't call it reduce, we call it simplify. And then we're going to learn how to add, subtract, multiply, and divide. Now this first part is review from grade 10, where we went from an entire radical to a mixed radical. And sometimes when we went the other way. What's an entire radical? It's just got a radical and something underneath. So square root 24. Cube root 25. Fourth root 26. Or like square root x to the third. You can even have variables. A mixed radical is made up of this and a number in front being multiplied. So it would be like 2 times root 24. 7 times cube root 25. Y times square root x to the third. There's something being multiplied in front. So what we learned last year to do with numbers, and now we're going to have some exponents this year, that's what's going to be new, is we learned to go from an entire radical to a mixed radical. And we learned it, well, let's, maybe before I say anything, do you remember how to do it? Almost. You've got the right numbers, you just don't quite have the right terminology. Excellent. These are ones when we simplify them by finding the highest perfect square that goes into the number underneath the radical or the radical. And remember the perfect squares, they're listed on the front page of this lesson. So I can break this down into the square root of 4 times the square root of 3. 4 times 3 is 12. Square root 4 times square root 3 is square root 12. Why did I do that? Because there's an easier way to say square root of 4, which is 2. And I can't do anything, we don't want to use a calculator and go to decimal. I can't do anything with square root 3, so I just leave it. And instead of putting the multiplication dot, I could just put them beside each other, and that means multiplication. So I went from an entire radical root 12 to the mixed radical 2 root 3. And remember, that's how you read it. 2 root 3. You would read this like root 12. Whenever it's a square root, you don't have to say square. You can just say the root. So apply that same thinking to B. 9 and 6. Therefore, it becomes 3 root 6. Okay, this next one, notice it's a cube root. So we need to break this down into a cube root of some number times a cube root of another number that gets me the cube root of 32. But this number's got to be a perfect cube. What are the perfect cubes? 8. So if this is 8, this must be 4. And the whole reason we did this is because now we can just take cube root 8 and make it 2. Can't do anything with the cube root of 4 unless we go to a calculator, but we're not going to do that. And we get 2 cube root 4. Try the next 3. Try the next 3. You may look at this one and say, oh, 4 times 20. And it does, it works, but it's not fully simplified. You need to find the highest perfect square. So you got to think of your perfect squares. Like if 4 goes into it, there, and if it's a fairly big number, there's a good chance 16 will go into it. And in this case, it does. The highest perfect square that goes into it is 16. So it becomes root 16 times root 5. So you got to be careful with that. And that becomes 4 times root 5 or 4 root 5. For the most part, there'll only be one perfect square that goes into this. But for some of them, you got to be careful. Like when you see 80 or 32, 48, okay? Those are ones that 16 go into, because if you think 4, if you're thinking 4 is the highest perfect square, just sort of in your mind check 16. Make sure that it is or it isn't. How about this next one? Yeah, root 4 times root 13. 16 doesn't go into this one. 4 is the highest. So it becomes 2 root 13. How about the next one? Root 100 times root 2, which becomes 10 root 2. Okay. Those are review. Now, newer stuff. What happens when we throw a variable with an exponent? Okay, let's walk through this first one again. First thing I'm going to do, remember, you can split any radical up into 2 radicals being multiplied together that gets that original. Like I could say root 10 is equal to root 2 times root 5. I can say root 15 is equal to root 5 times root 3. Root 28 is equal to root 4 times root 7. As long as those numbers underneath multiply to get what's in the original, I can do that. So the first thing I'm going to do is I'm going to split the number and the variable. So I'm going to make it like this. Square root 48 times square root x to the 6th. Whenever you've got exponents, split them first. It makes life easier when you simplify. Because then what we're going to do is we're going to simplify each one separately and put it all together at the end. Well, root 48, highest perfect square. Heard somebody say 16. Therefore, the other number must be 3. we can actually simplify these. This one I don't have to simplify because I can take the square root exactly. What is the square root of x to the sixth? Think of your first page. X to the third. Well, I can simplify a little bit more. The root 16 becomes 4. So I get 4 times root 3 times x to the third. The last step is take away the multiplication dots, put everything that's not under a radical together first. So I'm going to change this. Remember, when we multiply, the order doesn't matter. This times this times this is the same as this times this times this, or this times this times this. So I'm going to put the 4 first, then times the x to the third next, then times the square root 3 last. Why do I do that? I don't want to leave it in this order because I don't want to get confused that this would be under the square root. That's a new one. Yes, let me do it again. Let's do it again. But essentially that's it. So this one, first thing you do, split it. Root 24 times root x to the 9. And now let's just simplify each one. What does root 24 break down to? Say the perfect square first. Root 4, root 6. Okay, this one you can't take exactly. So you got to do the same thing. What's the highest perfect square that goes into x to the 9th? Well, what are the perfect squares again with exponents? X squared, x to the 4th, x to the 6th, x to the 8th, x to the 10th. What's the highest one that goes into x to the 9th? X to the 8th. How many x's are still left over? That's how you simplify an exponent under a radical. So now let's just keep simplifying. Square root of 4, 2, root 6, the square root of x to the 8. You can take exactly x to the, what times itself gives you x to the 8? X to the 4. You can't take the square root of x. Now, put everything that's not under a radical together first, then put everything that's under a radical together at the end. 2 times x to the 4. Well, root 6 times root x is just the same as root 6x. I can put them under one radical. Okay. You know what's missing from me? It doesn't say extend page. I'll have to look at that later. Interesting. It's a new version. Ooh, cube roots. Again, I see numbers and exponents split. Cube root 24 times cube root k to the 7th. Now you got to think perfect cubes. And again, go back to that list on the first page to help you if you need it. Cube root of 8 times the cube root of 3 for the cube root of 24. You can't take this one exactly because it's an odd number. So I have to think, what's the highest perfect exponent cube? Look at your front. What do you see? What will be the highest? 6. So k to the 6th, which means there's still 1k left. Now, keep simplifying. What is the cube root of 8? 2. I can't simplify the cube root of 3 anymore. What is the cube root of k to the 6th? K squared, yes. Well done. And I can't do anything with this. And now, everything that's not under a radical, put together first, and multiply that by everything that is under a radical under one radical. It'll take you a little bit to get used to, but that's how you do it. Split them up, simplify each one separately. If it's square roots, you're thinking perfect squares. If it's cube roots, you're thinking perfect cubes. The last thing I want to talk about, what if we were asked to go the other way? All those previous questions we just did. What if we started at the answer and I asked you, what was the original? Any ideas? This is a mixed radical. I want to write it as an entire radical. Right. If I can write this as a square root, can't I multiply those two together into a single square root? So 5 is the same as the square root of what? Well, how do you find that? Like I said, you do 5 squared. It's the same as the square root of 25. Times the square root of 3 gives me the square root of 75. That's an entire radical. So there's really nothing new here. We're just going in the opposite direction. Okay? Don't let any exponents throw you. You still do it the same way. I got to write a to the 3rd as a square root. Well, how do I write that as a square root? I got to do a to the 3rd times itself and put it under a square root sign. What is a to the 3rd times a to the 3rd? And I still have to multiply it by square root of a. So what is the square root of a to the 6th times the square root of a? No. Remember, this a here is the same as a 1. Square root of a is 7. Here you got to be careful because it's cube root, which means you've got to take this 4x and you've got to multiply it by itself 3 times. So you got to go 4x times 4x times 4x and put it under a cube root. (4x times 4x times 4x). 64x to the 3rd. And I still have to multiply that by the cube root of 2x. Well, I can multiply those into a single cube root by multiplying what's underneath. What is the 64x to the 3rd times 2x? 64 times 2? 128. X to the 3rd times x, or x to the 1st? And that's sort of the first step in dealing with radicals. Okay? Yes, we talked about stating restrictions on them, but this is kind of more of the meat of the lesson, is how to simplify.